In the earlier episodes, we have seen that metal casting was the oldest manufacturing technique. Even today, it is the primary manufacturing technique. The principle of making a component by metal casting is very simple. Whenever we want to make a component, a similar cavity we create in the molding medium, and the molding medium is made up of sand or metal or an alloy or a plaster or wax. The shape of the cavity will be similar to the shape of the component which we want. We melt the metal and we pour the liquid metal into the cavity. After some time, the molten metal will be solidified and we can take the casting outside. So, this is the simple principle of the metal casting. And to create that cavity, we use a model. We call it as the pattern. The pattern is the replica of the component which we are going to manufacture. And in the earlier episodes, we have seen the pattern material, pattern allowances and different types of patterns. We have also seen different ingredients of the molding sand and different properties of the molding sand. And we have seen different types of casting process. We classified into 4 types. One is conventional molding process, second one chemical sand molding process, third one permanent mold process, and fourth one special casting process. And in the conventional molding process, we use green sand or the dry sand as the molding medium. And the ingredients of this green sand are silica sand or olivine sand or zircon sand and some proportion of clay and moisture. And one of the drawbacks of the green sand molding is vapors are generated and hot gases are generated when we pour the molten metal. So, these hot vapors, if they do not escape from the mold, they create defects. Pin porosity or blowholes will result because of this moisture, because of these vapors. To overcome this problem, we incorporate dry sand molding, in which we dry the mold. Again, there are 2 types, in which we only dry the skin or the surface of the cavity. In the other case, we completely dry the mold. And the third one also we have seen the flaskless molding, in which we do not use any flask. And one of the drawback of the green sand molding and dry sand molding is it offers poor surface finish and the dimensional tolerance is poor. To overcome these drawbacks, we have developed shell molding, in which the molding medium is made up of resin, that is the mixture of phenol formaldehyde plus fine silica sand, and the pattern is made up of metal and the pattern will be heated. When we place the molding medium, that is the mixture of phenol formaldehyde and sand over the pattern, a thin layer of the resin melts and it forms a shell. Thus, we make 2 shells and we clamp them together and there will be a cavity inside. We pour the molten metal. So, that is the special feature of shell molding. However, this is limited to small castings. Maximum weight of the casting that can be made by the shell molding is about 10 kgs. Of course, this offers very good surface finish. Dimensional tolerance is very good, but this cannot be used to make large castings. And another drawback of the green sand molding is sometimes when we make the cores break because of the pore strength. To overcome this drawback, people have developed sodium silicate molding, in which the molding medium is the fresh silica sand and we add sodium silicate, and it again this is classified into two. One is self hardened and another one is carbon dioxide hardened. In the self hardened process, we add Portland cement or blast furnace slag and we allow it to set it. It takes about 24 hours time. Sometimes we used to bake it to get additional hardness. And in the carbon dioxide hardened sodium silicate process, we pass carbon dioxide gas through the mixture of fine silica sand and sodium silicate. This carbon dioxide hardens the mixture. And we have seen no bake molding, in which without any baking, within few minutes the system hardens. We use urethane and fine silica sand. We have also seen permanent mold process. In the case of the conventional molding process, the molding medium is made up of sand. And another drawback of this conventional molding process is, after solidification we have to break the mold. We have to take the casting outside. If we have to make one more casting, again we have to make the mold. The mold is not permanent. Every time we will be breaking. So this again and again making a mold takes lot of time and the productivity goes down. To overcome this drawback, permanent mold process have been developed, in which the molding medium is made up of metal or an alloy. The cavity will be engraved in the metallic boxes or the alloy boxes. The molding boxes are made up of metallic alloys. When we close the boxes, there will be cavity inside. We pour the molten metal. After solidification, we take the casting outside. In the case of the green sand molding, we are breaking the mold. Here we are not breaking. So this is the permanent molding process. And again this is classified into gravity die casting or pressure die casting. This permanent molding process is also known as die casting. In the case of the gravity die casting, the molten metal flows into the cavity by virtue of gravity. And in the case of the pressure die casting, we use external pressure to inject the molten metal into the mold cavity. So this is the pressure die casting. And we have seen different types of special casting process. One is centrifugal casting, another one is investment casting, another one is continuous casting, another one is plaster molding, another one squeeze casting, another one evaporative pattern casting, another one vacuum sealed molding, another one ceramics shell molding, another one slush casting. So these are all come under special casting process. Now let us see the centrifugal casting. Centrifugal casting. This was developed by A.G. Eckhart in England during 1809. In the case of the green sand molding, the molten metal flows into the cavity by virtue of gravity. In the case of the pressure die casting, the molten metal flows into the cavity by virtue of the external pressure that we apply. Here the molten metal occupies into the cavity by virtue of the centrifugal force. We cause centrifugal force on the molten metal. The molten metal goes because of the centrifugal force and it occupies on the mold cavity. So this is the principle of the centrifugal casting. This was first used in the 1800s. There are three types of centrifugal casting. One is true centrifugal casting, second one semi-centrifugal casting, and the third one centrifuging. First let us see true centrifugal casting. So this is the diagram of the true centrifugal casting. Here we can see the metallic mold. Here we can see the dark one, that is the metallic mold, and this metallic mold will be rotating. This is driven by a motor is here, a motor is driven, and here we can see bottom rollers, here one bottom roller and here one bottom roller, and there are also rollers, top rollers, here one top roller and here one top roller. So, this will be rotating at predetermined speed, and we pour the molten metal here through this pouring cup, and the molten metal flows and it flows into the cavity inside the metallic mold, and it rotates, and the metal spreads all over, and the metallic mold continues to rotate until it completely solidifies. After solidification is over, we stop the motor and we can take the casting outside. So, this is the basic principle. Let us see the step by step procedure. First one, we have to apply ceramic slurry to the mold wall. So, this is the mold, and here we have to apply ceramic slurry, because the molten metal should not be sticking to the metallic mold, and this ceramic slurry should be dried, and after the ceramic slurry is dried, it should be kept in an oven for baking, and the mold should be rotated at a predetermined speed, and the speed will be 300 to 3000 rpm. During that time, we pour the molten metal. The molten metal flows into the mold, metallic mold, and the mold is stopped after the casting is solidified. So, until casting is solidified, we should continuously rotate the mold, and we should note that no gating system is required. In the other casting process, gating system is required, but here no gating system is required. Directly we can pour the molten metal into the metallic mold, and after solidification, after stopping of the molding box, we can extract the casting from the metallic mold. So, here I am showing a photograph where the centrifugal casting is in progress. So, here we can see the metallic mold, and here we can see the rollers, and the molten metal is poured through this end, and it will be occupying all along the length. So, these are the some of the components manufactured by true centrifugal casting. Here we can see thick shells, and inside there is hollow cavity. So, these are manufactured by true centrifugal casting. And the other type of centrifugal casting process is semi-centrifugal casting. In the case of the true centrifugal casting, the axis of the molding boxes or the axis of the metallic molds is horizontal. Here the axis is vertical. Here we can see a pouring basin, and this is the casting to be obtained, right, and this will be rotating along a vertical axis, and this is the typical component manufactured by semi-centrifugal casting process. A wheel with some spokes, this kind of wheel is manufactured by semi-centrifugal casting process. And the next one, centrifuging. This is the third type of the centrifugal casting process. So, here we are going to manufacture small components, all are joined together and all are gated together, and this is a central sprue, and we can see so many castings are there and we pour the molten metal. As the molten metal is poured, the mold is rotating along a vertical axis, and the molten metal, because of the centrifugal force falling on it, it goes and occupies the extreme end of the mold cavity. We continue to pour the molten metal until all the cavities are completely filled with the molten metal. We continue to rotate the mold until the molten metal is solidified. After the molten metal is solidified, we can take the casting outside. Here we can manufacture number of components, small components at a time. So this is the centrifuging process, the third type of the centrifugal casting process. Now let us see the advantages of centrifugal casting process. Formation of hollow cavities without cores. In the case of the conventional sand casting process, if we have to make a casting with some hole, we have to use a core, and to make that core we have to put extra efforts. Sometimes it may break, that increases the production time, but in the case of the centrifugal casting process, there is no need for any core. This simplifies the process and it reduces the cost of production. So that is the primary advantage of the centrifugal casting process. And second advantage is regarding the elimination of slags and impurities. In the case of the conventional casting process, we make the cavity and we pour the molten metal. The molten metal is tapped from a furnace, and inside the furnace there is every chance that the molten metal may be mixed up with slag and other impurities. Though we take certain measures to segregate the slags and impurities from the molten metal, still there will be some slag and some impurity mixing with the molten metal. These small traces of slags and impurities come inside the cavity and sometimes they lead to defects. But here in the case of the centrifugal casting process, what is happening? The molten metal is subjected to centrifugal force, it is rotating, and if there are any slags are present in the molten metal, the slags are also subjected to centrifugal force. Molten metal is subjected to centrifugal force, slag is also subjected to centrifugal force. The density of the molten metal is high, the density of the slag is less. The centrifugal force falling on the molten metal is high, the centrifugal force falling on the slag particles and impurities is less. Because of this difference in the centrifugal force, the metal will be going towards the outer portion of the metallic mold, whereas the slags and impurities, they are subjected to small centrifugal force, so they will be inside the cavity or they are along the inner surface of the cavity. So in the case of the conventional sand casting process, we have to take extra efforts to segregate slags from the molten metal. Here, because of the centrifugal force, the slags are automatically eliminated, automatically they are segregated and they are collected at the inner surface of the casting. So they can be removed very easily, they are at the surface only. And in the case of the centrifugal casting process, there is no need for gating system. What is, hence casting yield is very high. What is this casting yield? Casting yield is the weight of the casting multiplied by 100 whole divided by the weight of the poured metal. Suppose if we are making a casting of 10 kgs, we have to pour more molten metal, because molten metal has to occupy in the sprue passes, molten metal has to occupy in the runner, molten metal has to occupy in the riser, in the gating system. So, more molten metal is poured than the weight of the casting. So, the casting yield is the weight of the casting multiplied by 100 whole divided by the weight of the poured metal. So, this is always less than 100%, usually it will be between 70% to 80%. But here in the case of the centrifugal casting, there is no gating system. So, casting yield is 100%. Of course, in centrifuging there will be central sprue, so casting yield may be little less, but in the case of the true centrifugal casting and semi centrifugal casting, the casting yield is 100%. And in the case of the other process, we used to cut the sprue, we used to cut the runner, we used to cut the riser. So, this is known as the fettling process. So, this increases the cost of the production, but here in the centrifugal casting process, there is no sprue, there is no riser, there is no gating system. So, no fettling process. So, the cost involved for fettling process is 0, and the casting is free of gas and shrinkage cavities in the centrifugal castings. Another one, fine outside details can be successfully cast. If the outer portion of the casting contains small details, sometimes it is difficult, but here we are applying centrifugal force. Because of the centrifugal force, the molten metal goes and occupies even into the small cavities. So, fine details can be successfully cast, and finally it is easy to inspect the castings, because most of the defects they occur on the inner surface. So, it is easy to inspect the castings. Disadvantages of the centrifugal casting, and here the segregation of the alloy component take place. Suppose if we are making a casting of an alloy, alloy means 2 or more metals may be present, the densities may be different. If the densities are different, the centrifugal forces falling on each and every element will be different. The centrifugal force falling on the metal which is having higher density, the centrifugal force will be more. If the other metal is having lesser density, the centrifugal will be less. As we keep rotating, as the centrifugal force is falling on the molten metal, because of the difference in the densities, because of the difference in the centrifugal forces, the alloy components may get segregated. So, we have to deal this situation very carefully and suitable only for axially symmetrical components. Of course, in this centrifuging it may be little exception from this point, but generally these casting process are suitable only for axially symmetrical components, and skilled workers are required for the operation, and sometimes inaccurate internal diameter arises. These are the applications of the centrifugal castings. Cast iron pipes with holes we can manufacture without using any core. Liners of IC engines, bushings, wheels we can manufacture by centrifugal castings. Pulleys and bimetal steel bronze bearings we can manufacture by centrifugal castings, and other parts possessing axial symmetry can be cast successfully by centrifugal casting process. So, we are studying the special casting process. We have seen the centrifugal casting process. Now, let us see the investment casting. investment casting. This investment casting process is one of the important casting process. Where extreme precision is important, we use investment casting process. That is why we also call it as precision casting, and the pattern material used in this process is wax most of the cases. So, we also call this process as last wax process. This process was originated in China during 1500 BC. Later, this was improved in Greece and Egypt. They used this technique for making art castings. This was rediscovered by B.F. Philbrook of Iowa in 1897 AD. As I have already mentioned, the common pattern material is the wax, and in special cases we also use frozen mercury, plastic and tin. Let us see how to make an investment casting. Step by step procedure. So, this is the component which we want to manufacture. So, this is the component. So, first we have to make the wax pattern. So, here is the metallic mold inside which there is a cavity, and the cavity inside this metallic mold is similar to this component, and we inject wax into this metallic mold. After wax is solidified, we take this piece outside. Next one, assembly, and if we have to make only one component, so that is not economical, we make several components together with a common sprue. So, here we have taken say 8 pieces, wax pieces, and we have assembled them. These patterns are assembled with a central sprue. Next one, shell building. We have to use one slurry. This slurry is made up of ethyl silicate plus fine silica sand, very fine silica sand. So, when we add this very fine silica sand with the ethyl silicate, it forms a fine slurry. We make a coating to this assembly with this fine slurry. Now, what happens over the surface of these pieces, wax pieces, the slurry coating is there. This fine slurry coating will help us to get the very fine surface finish, or it forms a fine shell outside the wax pieces. Next one, we make another shell, that is we use another ceramic slurry. Here we have used slurry made up of ethyl silicate plus fine silica sand, that is one slurry, and here we are using another slurry, that is the ceramic slurry. We dip this assembly into the ceramic slurry and we place it in the fine silica sand, or we sprinkle fine silica sand and it is dried. Again we dip this assembly in the ceramic slurry and we take it and we sprinkle the silica sand, and this process is to be repeated about 8 times. Means we dip it in the ceramic slurry and apply silica sand, dip it in the ceramic slurry, apply silica sand, and this cycle has to be repeated for about 8 times. Now what happens? A thick shell is created around the wax patterns. A thick shell is created around the ethyl silicate slurry coating. So now the next process is we have to dewax. In this assembly now there is a thick shell made up of ceramic slurry and sand. Inside there is wax pattern. wax assembly is there, that we have to dewax it. So we will be heating the system, the wax will be melting, the wax will be flowing out from the assembly, and we heat it such that even the small trace of the wax will not be present inside. The system is heated completely so that the wax is completely drained out. Now inside what is there? Hollow cavity is there. That is the negative impression of the system, negative impression of the assembly is inside. Next step, now we make a pouring cup. Now we pour the molten metal. The molten metal flows through the central sprue and it flows into each and every cavity, and it is filled with all the cavities, and after some time the molten metal will be solidified. After solidification is over, the next step, the knockout, means we break these shells and the casting comes out. Next one, we have to cut off. Actually our intention is not to produce this assembly, we want individual castings, right? So we want to separate this, so we will cut off using high speed friction saw, we will cut them each and every component. Now these are the components, these are to be given minor finishing operations. Once we give the minor finishing operations, the castings are ready. Advantages of the investment casting: this process offers excellent surface finish, very excellent surface finish, produces very fine details, especially if we examine some jewelry castings. The profile of some jewelry castings of or some jewelry items, the profile will be very complex. These complex details are cast by investment casting. And the next one is very thin sections can be made of the order 0.75 mm, and we obtain close dimensional tolerance. In the case of the conventional sand casting process, if we want to manufacture a certain component, the final casting that we will be obtaining will be little larger. The dimensional tolerance is not good, but here the dimensional tolerance is good. That is, the dimensional tolerance will be 0.08 to 0.1 mm. Complex shapes can be made, that is another advantage, and no finishing operation is required. Sometimes finishing operation may be required, that is very negligible, and castings obtained by investment casting, they are sound, usually they are free from defects. Let us see the disadvantages of the investment casting. Production of wax patterns makes the process costly. Yes, every time we have to make the wax patterns, and this increases the cost of production. Second disadvantage is the limitation, bigger castings cannot be made. The maximum size that we can make by investment casting is about 0.5 kg. Beyond 0.5 kg, it is difficult to make the casting, and the process is relatively slow. What is the process? First we have to make the wax patterns, next we have to assemble them, next we have to give a fine slurry coating. The slurry is made up of ethyl silicate and fine silica sand. Next we have to make another slurry, ceramic slurry. We have to dip the assembly in the ceramic slurry, and we have to give the silica sand coating. Again dip it in the ceramic slurry, give the silica sand coating. Then we have to dewax it. Then finally we have to pour the molten metal. So this takes lot of time. The process is slow, and incorporating the cores is difficult in the case of the investment casting. Applications: jewelry castings. In the jewelry castings, the profile of jewelry castings or the jewelry items, they are very complex. So we have to use investment casting, and they are made up of gold or silver, and we can't machine it. If we machine it, the chips will be lost. The chips of the valuable metal will be lost, so we can't machine it. the dimensional tolerance should be high. So, we have to use investment casting. Very high surface finish is required. So, that is why for making jewellery art items we use investment casting, and for making art castings also we use investment casting. And there are certain alloys which are very difficult to machine. These alloys can be successfully cast by investment casting. And milling cutters and other tools, they are made up of high speed steel. This high speed steel is very hard. Once we cast the milling cutter, if there is any irregularity, it is very difficult to machine it. That is why we cast the milling cutter by investment casting. Impellers and other components, they have very complex profile. So, these impellers can be cast by investment casting successfully. Jet aircraft nozzles can be cast successfully by investment casting. Parts of sewing machines, locks and rifles can be successfully cast by investment casting. And also this process is widely used in dentistry and for making other surgical implants. We can see here some examples of investment casting. We can see a few components and the shape is very complex, and in some cases the thickness is very small. So, all these can be successfully cast by investment casting. Here another example for the investment casting. So, this is the milling cutter. This milling cutter is made up of high speed steel. This milling cutter is cast by investment casting process. So, if it is made by other process, if there is any irregularity, if there is any extra metal, how can we machine it? It is very difficult. So, we do not want any irregularity, we do not want any extra projection, we do not want any extra material. So, this milling cutter is made by investment casting, by which we get the highest dimensional accuracy, we get the highest surface finish. So, no need to machine it, we only sharpen it before use. So, among the special casting process, so far we have seen centrifugal casting, investment casting. Now, let us see the continuous casting. Continuous casting. So, this was first conceived by Bessemer in 1858 and this gained popularity during 1960s. This is used to cast long ingots, square billets, etc. This continuous process is three types: vertical continuous casting, horizontal continuous casting and continuous casting in travelling mold. Let us see this process in detail. Vertical continuous casting. So, this is the vertical continuous casting system. The mold is made up of copper. Here we can see the mold. So, this is made up of copper and this is water cooled, and this vertical continuous casting is commonly used to cast steels. And let us examine the different components. So, here we can see the mold that which is made up of copper and it is water cooled, and its height is about 20 meters from the ground level. So, here we can see one X-ray transmitter and here we can see X-ray receiver. As here is the tundish means a special pouring cup or the special pouring basin, and we are pouring molten metal into this tundish. The molten metal from this tundish is flowing into the mold. As the molten metal flows into the mold, it is cooled and it solidifies. Here we can see this red portion is in the molten state and this blue portion is in the solidified state. So, as it solidifies, it continuously goes down. We can see here, we can see the rolls, these rolls will be rotating and the solidified casting goes continuously. And here there is X-ray transmitter and X-ray receiver, and inside there are any defects, any blowholes, and these will be detected online. So this is the purpose of the X-ray transmitter and X-ray receiver. And here is the starting dummy. Initially this starting dummy, it is at the top. So over this starting dummy we pour the molten metal, and this starting dummy slowly comes down. As it slowly comes down, the molten metal is solidified, and as it is solidified, it is rolled, slowly it is rolled, and the whole structure comes down. And when we are pouring molten metal into the mold, there is a chance the atmospheric oxygen may react with the molten metal and oxides will be formed. So this has to be avoided, this has to be prevented. So we are passing argon gas over this mold. So this argon gas prevents oxidation. And also we use some lubricating oil, we send some lubricating oil so that the molten metal will not be sticking to the mold. So this is the system of the vertical continuous casting, and here we can see the process in further. So here is the ladle and this is the tin dish, and we are pouring molten metal here and it is solidified, and we can see so many rollers, and here it is cut, and they are sent for further heat treatment operations. And here we can see the way the solidified billet is coming down. It is solidified and it is coming down continuously. Sometimes even parallelly more than 2 billets will be coming down, 2, 3 or 4, 5 billets will be parallelly cast. Yes, here we can see 4 billets are continuously cast, parallelly cast, and they are coming down. As they come down and they are cut and they are sent for heat treatment operations. So this is the plant. So here we can see the mold is kept at an elevated position and it is solidified and it is slowly coming down, and here it is cut and they are sent for further heat treatment operations. Next one, the horizontal continuous casting. This process uses a graphite mold, and this is commonly used to cast non-ferrous alloys. And here is the holding furnace, there is molten metal here, and this is the mold, this is water cooled, and here there is another cooling system, and here we can see as the molten metal is passing through the mold, a bar is generated. So this bar is fed continuously outwards by these rollers. So this is the horizontal continuous casting. And continuous casting in travelling mold. In the case of the vertical continuous casting and horizontal continuous casting, the mold is stationary, and here in the continuous casting in travelling mode, let us examine. So here is the molten metal coming from the furnace, and this is the tin dish, and here we can see a nozzle, and where is the mold? So here we can see belts. These belts are rotating like a caterpillar, slowly they will be rotating. This is rotating in this direction, this is rotating in this direction. These two rotate like a caterpillar. So the molten metal is trapped between these two belts, and slowly they will be advancing. As they advance, it will be cooled. By the time it comes out, it will be solidified. We can see cast strip is coming out, and the casting rate is 0.5 to 10 meters per minute. Maximum width of the cast slab is 1.75 meters. The slab gauge is within the range of 10 to 40 mm. So this is about the continuous casting in travelling mold. Advantages of the continuous casting process. First advantage is 100% casting yield. What is this casting yield? We have already seen, again I will tell you. Casting yield is the weight of the casting multiplied by 100 divided by weight of the poured metal. Yes, weight of the poured metal is always more than the weight of the casting in the case of the conventional casting process and many casting process. But here there is no gating system, there is no sprue, there is no runner, no riser. Whatever we are pouring is becoming part of the casting. So here we are getting 100% casting yield that decreases the cost of production, and it is cheaper to produce the ingots. Ingots can be produced by rolling also, but the cost involved in rolling operation is more compared to the continuous casting process, and here we get better surface finish. Grain structure can be regulated, process is automatic. Here we have seen the process is automated, so less labor are required. At stage may come where there will be scarcity of labor, at such times this process will be highly useful. Applications: long billets of any cross section can be obtained, whether it may be round or square or hexagonal or gear teethed. Any shape ingots can be obtained by continuous casting, and solid castings can be obtained and hollow castings also can be obtained. Bushings and pump gears can be made by continuous casting. Production of copper bar or wire can be manufactured by continuous casting. And here I am showing you an example. So this is an example, this is a gear produced by continuous casting. It means we can see so many teeth for this gear, means this kind of long billet is produced by continuous casting. So this is without machining. Immediately after casting we have cut it, but after machining we get a fine surfaced gear. So this gear ingot is manufactured by continuous casting. So among the special casting process, we have seen centrifugal casting, we have seen investment casting, we have seen continuous casting, and in the centrifugal casting we have seen that it is of three types. One is true centrifugal casting, semi-centrifugal casting and centrifuging. We have seen investment casting and its special features. We use investment casting where extreme precision is important, where extreme surface finish is important. We use investment casting, and we have also seen continuous casting and its three types. One is vertical continuous casting, other one horizontal continuous casting, and the third one continuous casting in travelling mold. We have seen its applications, and in the next episode we will be seeing the other special casting process like plaster molding and squeeze casting, etc. Thank you. Thank you.